All right, so now let's actually introduce the Fourier series now that we have the intuition behind it. And first thing I should say is, if I ask you who discovered the Fourier series, you're probably going to say Fourier. Actually, it was pretty much Gauss and Euler, although there's this rule in math, if Euler came up with something, it doesn't count. It's this next person after it, because he just did so many things that basically if if he was the first person to do it and everything would just be named after him, it'd be confusing. So basically it's now the next person who discovered it after him. So we talk about the Fourier series even though Euler was the one who did most of the stuff behind it. Now the Fourier series, as we talked about, is trying to represent our signal as a set of basically these exponentials. And what I'm going to do here is I'm going to write a signal as a function of time, s of t. And I'm going to, for this case, assume that my signal is periodic, meaning it has some periodic with period t. And this is just going to help make things easy. Now, one of the things we will do later is we'll just basically say, yeah, it's periodic with period t, but as we let big T go to infinity, we kind of can we can simplify things by taking the limit as it goes to infinity. So don't worry if your signal's not periodic. This is one way to kind of think about it. You can kind of pretend it's periodic outside of the range that you care about in it, and then you can extend this idea. So right now, let's just assume it's periodic with some real value period. The Fourier series is simply the sum, and I'm going to use k as my indexing variable, from minus infinity to infinity. So it's an infinite sum of c sub k e to the j 2 pi kt over big T. So what's going on here? Well, we are writing our function s of t now as a sum of these ck's, these are complex numbers. So I'm going to write this as basically big C with the line in it. This means it's a complex number, so it's a plus bj, and the c is just because it's a coefficient, and times this exponential at a given, I guess, integer multiple of the period. So basically what's going on here is as k increases, maybe what's best to do is if we have 0 to t, here's t, and here's 0, what you're going to see is, of course, something like this, and then you increase k, and you'll get something like this, and then you'll do double this, so et cetera, et cetera. So this is what you see, and then of course the minus side you're going to do it in the other direction kind of as well. So that's what's kind of going on here. You're basically having these exponentials. I'm really just plotting the. Well, I guess this would be kind of the imaginary part, but you kind of get the idea. This is using Euler's expression. You have e to the j theta equals cosine of theta plus j sine of theta. So once again, what I'm doing here is at each point, this exponential is going to give me an imaginary and a real part, and it's going to be at a given frequency k. So as we change k, as we increase it, these are going to get tighter and tighter together, and then ck is just simply the amount. So these are often called our basis functions, and this has to do with the way it works in linear algebra, where we're writing our function not as a basis in terms of time, but a basis in terms of frequency, and then we just add together. So these are kind of like what I would say, these are like your ingredients. And then the ck's is like how much, ck for a given k is telling me how much of that particular ingredient. So if ck is 0, it's like, don't add that ingredient of the frequency, of the exponential of the frequency k to build my signal s of t. So what we're doing is we're moving from s of t now into an indexed sequence c sub k, but it's an infinitely long sequence that goes from minus infinity to infinity. So what you get is, it's going to have values at each particular point, -1, 0, 1, 2, etc. And if we want to get back to the time domain, we simply go back. So now, once we've written our signal this way, if we want to take the derivative, the ck is just a coefficient, right? So it doesn't matter. And then what you do is you get, if you take the derivative of this, so, d dt of s of t is equal to, well, the derivative is linear, so the derivative comes inside the sum, minus infinity to infinity. C sub k does not depend on time, so C sub k is out here. And then all we need to do now is just make sure we are doing the chain rule right. So what comes out here is everything that's not dependent on t. So what you have is times j 2 pi k over big T times e to the j 2 pi k t. So this is sort of like my constant. And if you wanted to hit it with another derivative, so d squared dt squared, you would just square this particular value, and so on and so forth. Now this is easy. Remember, the ck, it doesn't depend on time. And similarly, if you wanted to take an integral of s of t, well, integral's linear, so it comes inside the sum. A sum of integrals is the same as the integral of sums. I mean, basically the integral is a sum. It's a limit of a sum, so you can swap sums around. It doesn't matter what way you add them. This has to do with basically commutativity of addition. And once again, ck doesn't depend on time, so we're integrating over time, so it's a constant with respect to the integral. So ck comes out, and what do we get? Well, we take the integral of this exponential, and what we're going to see is we're going to get basically the opposite, because we get 1 over this particular thing. There should be a t here. What you get is t over j 2 pi k, or you could just basically say this thing we had up above to the minus 1, e to the j 2 pi kt over big T. So notice how if you take a derivative and then take an integral, these basically cancel each other out, as we expect from the fundamental theorem of calculus. And as before, you can add a bunch of these if you want, and all you do is you just take this and you add it to whatever power of however many integrals you want to do. So this is pretty nifty. So hopefully you see why it's really nice to represent your signal as a sequence of c sub k's rather than a function of time. Now the question becomes, how do we actually calculate the c sub k's? And the way you do it is by finding the Fourier coefficients. And this is done by the following expression. C sub k equals 1 over big T, so we're dividing by the period, the integral from 0 to t over the entire period of my signal. So after it, it's just going to repeat. So we're just going to look at a small portion of it where it is repeating. And we're just going to have s of t e to the minus j 2 pi k t over t. And this is with respect to my function of time. So I am doing this. Now, where does this minus sign come from? What's actually going on here? Well, what we're actually doing is we're doing what's called an inner product. What we're trying to do is find how much my signal is aligned with this particular function at any given point. And when you take the inner product of two vectors, x and y, say, if x and y are on the same line, then the inner product is going to be pretty big, basically multiplying them together. However, if instead my signal is orthogonal to the other vector, meaning if my signal is not in the direction that I'm looking for its component in that direction, what I'm going to get is 0. So, if I take the inner product of two vectors at 90 degrees, then I'm going to get 0. If they're in phase, I'll get basically a large number. If one's pointing the opposite direction, that'd be like, over here, then you're going to get a negative number because you're basically saying I'm going, a lot, but it's in the other direction. So it becomes negative. And when you take the inner product with complex numbers, so the inner product of two complex vectors, this is like a vector of time. This is a vector of time. What you do is x comma y is equal to, basically, you could say if this is discrete, it's just the sum from, you could say I equals 0 to infinity of x of I, y of I, conjugate, or you could say x conjugate. It doesn't matter. You can just swap them, right? The inner product, x and y, doesn't matter which direction you have them. Now, of course, if it's completely real, then you don't have to worry about the conjugate, which is why it's usually presented in some other way. Or of course, if they're continuous values, what you get is the integral from minus infinity to infinity, or the integral from 0 to infinity, once again, depending on how this is indexed. But notice that we're taking the inner product with respect to two functions of time, so we need this to go over our time, we're integrating over time. So this is going to be just basically x of t times y of t conjugate dt. This is how we take our inner product. So basically what we're saying is hey, take the inner product, find out how much my signal, s of t, how much of this particular component I would need to add to this signal, and that's going to give me my coefficient. Now this is called the analysis piece, where we basically are determining the c sub k's by basically saying how much of this ingredient, how much of this particular exponential at a given k I should add to be able to reconstruct s of t. And then once you have the c sub k's, you do what's called synthesis to get back to s of t, because what you're then doing when you look at s of t as this particular thing is you're saying, all right, give me back this particular function at this value. So that's kind of what you do. So this is the main principle behind the Fourier series. Hopefully this is helpful. You understand the way this works. One thing that's important to note, and we'll talk about this later, is these different exponentials are actually orthogonal to each other, which is what really helps. And I'll show that in the next video. But hopefully here you now understand both what the Fourier series is. Once again, it's writing our signal as a function of what frequency ingredients I would need to add to be able to reconstruct my signal once I eventually want to get it back in the time domain. But once we have our c sub k's, it's very easy, once we've written it as a function of these exponentials, to do things like derivatives and integrals. See you in the next video.